first presentation I didn't get to, which is crucial for what I want to do next. So, where I want to get to is the idea of reformulating a PDE which has some random inputs as a so-called parametric PDE. And in a nutshell, what this means is I can't assume that now that the randomness enters my problem in an abstract random field sort of way. I'm going to assume that the randomness now enters my problem in a very structured way that allows me to do this reformulation. So here's our model problem right at the top again. So it started off life where I said, well, let's just, as a thought experiment, assume that my diffusion coefficient, my spatially varying uncertain function here, is some random field. And I've now kind of surveyed a bunch of numerical methods that you could use to simulate kappa from, let's say, a Gaussian or a log normal distribution in a couple of ways. So to move towards the numerical methods that I want to talk to you about, which are very different in nature to the Monte Carlo method, I'm going to need to make this assumption now, which is often called the finite noise assumption. I'm going to assume that my random inputs are functions of a specific set of random variables, psi1 up to psi j, which I'll just collect together into a vector and then call that bold psi. So that means I'm not going to work with grid-based representations of random fields from here on inwards. I am going to assume more that I have this sort of series representation of my random input, like this Gehuna-Lerve type expansion that we saw, and that I've chopped it off after j terms. So my random input is now characterized by an expansion, a Fourier series type expansion, which is a function of j specific random variables whose distribution I know. Right? So in a nutshell, if my inputs to my model are functions of j random variables, xi1 to xij, then assuming my problem is well posed, the solution is also going to be a function of those random variables, right? So my solution is not going to be random in an abstract way, it's actually going to be a function of those variables. The mathematically more sophisticated way of saying that is, if the solution is measurable with respect to a sigma algebra generated by those random variables, then it can be expressed as a function of those random variables. That's just a sort of a fancy way of saying it, that if you write down a weak form of this problem, then for the probability distribution that this thing has, if you can show that that problem is well posed, then you can write it as a function of those variables. And this is what allows us to reformulate the problem as a parametric one. So it's going to be like a change in notation here, which is really just like a change of variable in an integral. I'm going to let yi be the image, formally, of the random variables that characterize the uncertainty in my problem. Now, different bits of the literature sort of oscillate between parameters and random variables, but I'm going to use the language of parameters. So bear in mind that these yi's are images of random variables which do have a distribution associated with them. So the distribution will play a role somewhere. And we're going to now, instead of just writing our problem down this way, as if we had an abstract probability measure or an abstract random field, I'm going to say, okay, I've got structured randomness, and I'm now going to reformulate my problem in this way. Right? So what we're looking for now, so note the change in notation, my input k and my solution p are now functions of x as they were before, but now I'm writing them formally as a function of these parameters y, which are like the images of my random variables. So y, as a vector of parameters, will take its values in some set, which we typically call gamma, which we call the parameter domain. And basically this is just a set in which all the samples of your random inputs take their values. So in other words, if you had a set of j uniform random variables, so minus 1, 1, then gamma would just be minus 1, 1 to the power j. Right? That's the set. Once you've chosen your distribution for your psi, then you know what that set is. And for which you pick the distribution for your random inputs, so we know what that set of gamma is going to be. That's going to depend on the distribution of these things. And then look at the way I'm phrasing the problem now. Again, this is just an alternative way of saying with probability 1, I want my PDE model to be satisfied. I'm just going to write it with this notation where rho now is the probability density function associated with this vector of random variables. Okay, so this is just the parametric way that we write down the same problem that we had before, but when we just have more structured randomness. So the key option notation is the gamma, which is now the parameter domain. the set in which all my random variables take their values, and rho of y is going to be the joint probability density function associated with my vector value random input. Right? So hopefully everybody knows that even though p started off life as a function of psi to compute its expectation, formally it's an integral over the sample space with respect to the probability measure associated with this, but we can just formulate it like this as an integral with respect to this probability measure on the image space. Right? So might as well just use that and rephrase everything now in terms of y rather than psi. Right? So the key thing is now I'm going to view my model. Now that I've used this way of modeling the random inputs, I'm going to just formally view the PDE solution as a function of space as I had before, but as a function of j parameters that are associated with my input distribution. This is what we mean by a parametric PDE. From this point onwards, I'm going to talk about numerical methods for doing forward UQ for parametric PDEs. Right? So this is where the problem comes to you after you've already done this modeling step for your input randomness. If it's not appropriate to encode your uncertainty this way, don't use the methods that I'm going to talk about in the next session. Monte Carlo is more forgiving, it's more flexible. You don't have to have your problem in parametric format to use a Monte Carlo method, but you do for the methods that I'm going to talk about next. You have more structure, then let's leverage that. So, just a note on parametric PDEs. If you look in the literature, just do a Google Scholar search for numerical analysis parametric PDEs, you will find bazillion papers about this scalar elliptic problem with coefficients that look like this. Okay? We often call this an affine parametric expression. So lots of people have analysed to death, myself included, that's no criticism to anybody else, problems of this nature with coefficients that look like this. So we've got like a leading term, which I'll call K0, which has got no parameters in it, so that's like the deterministic or the mean part of the field. And then this sort of random part, which is associated with the non-zero mean part. And so often we assume that we can write this part as a linear combination of some spatial functions times these parameters, which are associated with the uncertain part. Yeah?
And on the slide before, where you rewrote the expectation, what did that in the last slide? So what does that tell me that I can rewrite it like this?
That's just some basic probability theory that says if I want to compute the expectation of p, and p is a function of psi, then that is formally the definition of expectation, right? Yeah. Okay? But in order to do that, you need to know what this is and you need to know what this is, right? Yeah. But if we know the probability density function associated with this, and usually you do a basic course on probability, you'll kind of not learn that. You'll just say that's how you compute the expectation, right? You need to know the joint probability density function, and then there's really a change of measure that goes from here to here, right? This is like an integral change of variables, effectively, right? dp can be written in terms of rho y versus now the Lebesgue measure, right? So I just need a bit of basic probability theory to say that that's how expectation can be computed. And so if you close the eyes to this, you might as well just view p as a function of y. Does that make sense? So, and that's what I'm going to do from now on. Because for stress, I can only do this if I've first been through this modeling step to encode or to characterize or express my uncertainty in my spatially variant random input with a set of such parameters. So, in a lot of my examples, you will see me just abstract the coefficient up to this level of abstractedness. And so I just want to tell you, sort of, or emphasize why or when such a structure may exist. Because the approximation theory, you open a numerical analysis paper and you kind of find some error bounds and so on, the style of presentation won't necessarily care about the application, it won't necessarily care about what the covariance function is. It's all about exploiting structure when it comes to approximation theory, right? So if you have a class of inputs with that structure, then the analysis is often done in terms of having that structure and making certain assumptions about the parameters or about the spatial functions. So and the analysis is often abstracted away. So when do structures like this occur? We've already seen one such way. There are two common sort of scenarios when this sort of structure occurs. One is where you might just have piecewise defined coefficients. So for instance, if these things were spatial indicator functions associated with different spatial domains, right? So we could have this scenario. So what I'm saying, if yi actually just represents the value of k in one subdomain here, right, then I could express k as a linear combination of indicator functions, meaning that this is the function that's 1 in the ith subdomain and then 0 everywhere else, right? That would be a way of expressing a spatially piecewise constant discontinuous but uncertain coefficient as an affine function of 5 parameters. Okay? So they would be spatially discontinuous. Or, well, the scenario that I'm going to work with is the one that we've already seen. So if you use one of these coherent level expansions to represent a random input, remember the expression in the box that we had before. If I truncated it after j terms, and remember j may have to be very, very large if you have a badly behaved covariance function or lacking regularity behind the scenes, right? But we've already done that step and assessed how big j needs to be. Then formally we have an input to our PDE, which is a function of j parameters. Okay? So this is more the scenario I'm thinking about, but in the analysis often, they're not really telling you where the application comes from. They just kind of say, I've got an expression of this form. But for us, if we're working in this setting, then the functions in this coherent-Lerwick setting would be these ones. So each of the coefficients would involve an eigenvalue and an eigenfunction from the decomposition of the covariance. And a key thing to take from the session before was that because these things decay, then if you kind of take the sequence of functions and take their norms, the analysis will require that as a sequence they decay at some rate. Right? So in the analysis, you'll often see a statement like, let's assume my coefficient looks like this, and let's suppose the sequence decays at some rate. And if it decays at some rate, then we can prove something where the final result will depend on that rate of decay. Right? I'm not going to be too specific here. I'm just going to say KL expansions of that form have this structure, and then I'm just showing you some samples of a truncated expansion. Okay. So that's kind of where I'd hoped I'd got to at the end of the last session. So that in this session we could get started then on talking about some methods for parametric PDEs, which are known as surrogate modeling methods. So here's my parametric test problem again, right? Don't worry, I'm not only going to solve this problem, but it is the simplest one to describe, so we'll start from this one. So here's my toy parametric problem. No omegas or abstract probability measures anymore. I've got a specific set of random variables, and I'm just doing a change in notation. And I'm going to view my input and my solution as a function of these j variables now. We've got my parameter domain. Right? And somewhere behind the scenes, we've got a probability density function associated with the distribution of the original random variables I was working with. So in the parametric setting, we're just going to view this as a high-dimensional PDE. We've got a solution, P, which is a function of x, so let's say I'm 2D in space or 3D in space, and j of these other parameters as well. Right? So we've got a solution, which is a function of many, potentially very, very many variables. Okay, if I use the full coherent love expansion for my k, then actually I've got infinitely many of the y's, right? So it really is a high-dimensional problem. Okay, so in the literature, again, this often comes under methods for high-dimensional PDE, parametric PDE. So the aim then is to approximate quantities of interest related to solutions of parametric PDEs that look like this. I will assume at some point that my y's are connected to random variables that are independent, but we'll see why that's the case later. So, in the grand scheme of things, numerical methods for parametric or random PDEs or whatever you want to call them, there are many. There's a zoo of methods that you could use. And I guess what I want to do is not just tell you about all the state-of-the-art methods. I'm just going to talk about some of the basic ones and then build up to something a bit more sophisticated. So here are some methods. You'll notice I'm not saying machine learning anywhere because, just kind of doing us out of business these days. So we could add machine learning to this list, but we're not going to go there in this section. So here are sort of like the basic ones. You went to a SAM, conference, you'll be people using all these kinds of methods. So Monte Carlo, we already know about. In this session, if I leave myself enough time, I might not do. I want to introduce you to the idea of something called a reduced basis method and something called stochastic collocation. And then tomorrow I'm going to focus on the method at the bottom, which is the stochastic Galerkin method. So when we characterize or we classify methods for doing UQ, we usually label our methods with these two keywords. Is it a non-intrusive method? Is it a surrogate method? So all of the methods I've highlighted in blue there, we've got yes in the surrogate modelling column. So what's a surrogate? So in the context of parametric PDEs, a surrogate method gives you an approximation that is a function of y. Monte Carlo method is not a surrogate modelling method because what you do is produce samples. It's not a function of y. We want to treat the solution to this problem as a function of x and y. Right? So what we will get back out of it is a function of y, so something that once we've built it can be queried for a new choice of y without solving the PDE any more times. Right? So it's if we're approximating all realizations of all samples of the solution simultaneously. That's effectively a surrogate modelling method. And then the other key thing is a non-intrusive method. So I don't like to like this word. Non-intrusive basically means you don't have to do any coding, right? What it means you don't have to like intrude on your code, right? It means that you can make use of any code that you have for the deterministic problem already. Or if you wanted to kind of be a bit fair, you could say it means I only need to reformulate my problem. Like just sort of at the level of implementation, I just have to solve my deterministic problem for different choices of my inputs. So at the level of implementation, it's more like a sampling-based method. Hopefully it will become clear what that means as we go along. The Monte Carlo is definitely non-intrusive. You've got a finite element code, good to go. You just put in different samples of your inputs. Nothing special you have to do. Reduced basis and stochastic collocation, the two methods I'll try and tell you about now, they are also non-intrusive at the level of implementation. The method I'm going to tell you about tomorrow has got a big fat no. It's not non-intrusive, that means it is intrusive. People don't like it for that reason. Okay? So for today we'll stick with non-intrusive and then tomorrow we'll get to the sort of less popular intrusive method. Okay, so what I have in mind for today, let's see how far I get. Hopefully I can go through this first part quickly because Rob set the scene this morning. All of the methods I'm going to talk about have Galerkin approximation at the heart, so it's worth just re-emphasizing what is Galerkin approximation and why we like it so much, and why it sort of is around, permeates the field of numerical analysis. So I'll go over that quite quickly, and then I'm just going to kind of teach you the basics. Again, people who work on these, I'm an expert on neither, I should say. So Fabio Navilla is one of the numerical analysis who's written a lot of work on stochastic collocation. So if you've got any really hard questions, you should ask him. I just want to kind of show you how you can take either of these approaches and build a surrogate using a sort of a sampling kind of technique, which for some problems might be a smarter thing to do than using Monte Carlo with a finite element method. Okay? And then I'll just illustrate these methods with some toy examples. Okay. So again, stop me if you've got any questions, that's fine. So let's start with a Galerkin approximation then. And just backtrack, remember we want to do parametric PDEs, but I'm assuming everyone is familiar with Galerkin approximation for deterministic PDEs. So let's take the y and the random variables out of the equation, and then we'll put it back in afterwards. So Rob went through this, so hopefully this is now clear. But my notation might be a little bit different. If my domain is now d instead of omega, my coefficient is now k instead of a. Okay, so if we've got nothing's uncertain in my problem, if I know what k is and what f is, and I've got zero boundary conditions, the standard way to approximate the solution to this problem for a numerical analyst is to first set up a weak formulation of the problem, right? In order to set this up and to prove that the weak problem is well posed, we need some assumptions on our inputs. So we know that if f is in L2, and if our coefficient satisfies this condition that Rob wrote down earlier, so that means it's in L infinity, and it's bounded below, then we can show that this weak problem that I've written down here, we can show that it's well posed. So let's just remind ourselves to cook up the weak problem. What do? We take our PDE, we multiply both sides by an appropriate test function. So in this case, the appropriate class of test functions would be the space H01, right? And then we manipulate things using things like some standard results from functional analysis. We apply integration by parts, apply any boundary conditions we have. In this case it's 0, so that's easy. And we use the Lax-Milgram lemma. So notice that we commonly hide away all the details here by just saying, okay, that's a bilinear form, that's some sort of linear functional. And we abstract it away again and say, okay, we've got a problem with that structure. We have a problem with that structure and those conditions are satisfied. Lax-Milgram tells us all these things. Tells us our bilinear form is coercive, it's bounded, as long as the assumption on our coefficient was satisfied. Our linear functional on the right-hand side is also bounded with some standard results if f is in L2. And if that condition on A is satisfied, here's something slightly different to what Rob said, then it's an inner product. And that inner product induces a norm, which is often called the energy norm. So Rob was working in the H1 norm. The H1 norm is related to a different inner product. Does that make sense? Because sitting inside the A, we've got our coefficient. So the energy norm is a norm where we've got the coefficient sitting inside here. So this is more like a weighted norm, a weighted H1 norm. And when I'm talking about errors, I will often be talking about this norm. And hopefully when you do what you want to do, you kind of be clear about what norm you want to assess the error in. But this is a nice norm to work in if you're working in a Galerkin framework. Right? So we haven't done any Galerkin approximation yet. This is just to set up the weak problem. And again, just to emphasize, if we make K random, and we make K a parametric problem, we have to go through this again. We have to set up an appropriate weak form, we have to identify appropriate function spaces, we have to make sure that we put the right conditions on K to make sure that the conditions of the Lax-Milgram lemma are satisfied, and we have to identify an appropriate norm that we want to measure our error in. So where does the approximation come in? So Galerkin approximation just says, okay, you come along, and if you want to do computations with Galerkin approximation, you have to choose a finite dimensional approximation space. I'm going to call it V hat here. Not necessarily have to be finite elements, but let's call it V hat, which is a linear subspace of V, and it's n-dimensional. Right? So Galerkin approximation just says, you give me some finite dimensional subset, V hat, if it's a conforming setting, and then you just project the problem down onto that finite dimensional space. That's Galerkin approximation. And it's very general. And they typically work with finite elements, but it could be more general than that. So in this setting, for these kinds of bounded coercive problems, there isn't really any extra conditions that you have to satisfy. As long as V hat is a subspace of V, you're good to go. And you know all the conditions are inherited, and that this weak problem on the finite dimensional space is still well posed. Okay? So why do we like Galerkin approximation? Alright, so I need you to remember this for tomorrow. So if you just subtract the two equations, we have this thing called Galerkin orthogonality, which Rob mentioned earlier. It tells us that the error between P and our Galerkin approximation is effectively orthogonal to everything in our approximation space in this inner product. Yeah? Because of that, it tells us that our approximation in the energy norm is the best from that space. Because Rob was working in a different inner product with a different, which didn't have the coefficient in it, didn't quite get the result as clean as that, right? And was using Sayre's lemma, you just get the energy norm is the best, right? Of all the functions in V hat that we could compute, the one that falls out of applying this Galerkin condition is the best, in that the energy norm of the error is smaller than it is for any other function in that space. So that's good, that's why numerical alignment like Galerkin approximation. It does not tell you that the V hat that you chose was a good space. It just says once you fix that space as the space that you're searching for your approximation, the one you're going to compute is the best in that space. Couldn't be a lousy space. Okay? Which you have to worry about at some point. But this is why we like Galerkin approximation. Okay, so what's the work involved? You have to solve a linear system. Rob said this morning. So we're computing a function, but what falls out of that mathematical equation is a linear system of equations that you can solve to find the coefficients that represent your Galerkin approximation in your chosen basis. The bottleneck, right, is solving this linear system of equations. The work involved in a finite element method is solving a linear system. Okay, so what are the things to consider? The properties of this matrix will be inherited from the original PDE and the approximation space that you chose. So in this scenario, all we have to do is check the conditions on K. If K is bounded below here, it's a strictly positive function, then that A is going to be a positive definite matrix. It's going to be a symmetric positive definite matrix, and that will guarantee that it's invertible. So typically, if you work with a K that doesn't satisfy the right conditions, when it gets to solving a linear system, you'll often get an error message, right? So as long as you respect the conditions on your input, usually you'll be able to solve this linear system. Okay, well, is it a big deal or not? Well, n may be very large, especially if we have things like small correlation lengths and so on. But for finite element spaces, we do know that these matrices are sparse, which is always a good thing in linear algebra. If your matrix is large, okay, sounds like a problem, but it's really sparse, and you can leverage that, then that might be okay. But the best we can usually do for an n by n system, capital N, is to solve the system in an amount of work that scales linearly with n. That would be like usually the best that we could do for a sparse matrix. And that's usually what we try to aim for. Right? So if an optimal solver is available, then doubling n by a factor of 2 should lead to no more than a factor of 2 in the increase in the work that I need to do. But n is a big factor or consideration when it comes to like the work involved in solving these linear systems. Okay, and just to remind you that if we do choose to use finite elements, which is what I'm assuming, is that these are what my basis functions might look like. This is the problem. We know from the back of the envelope analysis, if I can call it analysis, that you did on the last slide, that's what gets you into trouble. So reduced basis methodology says, okay, the Galerkin approximation is more general than that. Right? I'm going to assume we're using finite elements. Okay, so the first non-intrusive surrogate-based method I'm going to talk to you about is something called the reduced basis method. As I said, I'm not an expert in this. I have used these methods and have some hands-on experience of them, so I'm going to share that with you. If you want to get into this business into way more detail, there are 2 books that I can recommend, both published in the same year, both published by the same publisher, both published by people working in the same group at roughly similar institutions. So there's a story somewhere there. But one is by Quattroni and Co. One is by Gianluigi Rozza and Co. So in particular, Gianluigi, some of you may know him, has a big group at Trieste and Sissa, where they have a lot of work on lots of problems about these kinds of methods. So in particular, I would sort of look at his group's work if you want to get into these methods in more detail. So let's go back to our simple parametric elliptic problem again. So remember, I just sort of talked to roughly all the things you need to worry about if you want to do Galerkin finite element approximation for a problem when nothing is uncertain. Now we're adding uncertainty back into the problem. So now we have a diffusion coefficient which is going to depend on some parameters. J may be very large, right? And we have a solution P which is also a function of these parameters as well. So if we do what we did in the last session, just use a Monte Carlo method, basic Monte Carlo sampling with basic finite elements, whack them together. You already know that's a bad idea, but let's think about what you now need to worry about. Well, using a sampling method, then for each new y that you've chosen, you have to worry about whether this is an appropriate function or not. Does this satisfy all the conditions for every sample of y that you needed to check on the last slide for all your problems to be well posed? So if you use the wrong distribution, it may be that this is not a strictly positive function, right? So that places some conditions on the kinds of functions that you can work with. Well, let's say you've taken care of that, then for each y, your sampling method says you need to solve your problem at, you've got to solve a linear system. Right? That's the bottleneck. So for n samples, even if you have an optimal solver for this problem available, this is an n by n problem, that's the best that you can do. This is the problem. We know from the back of the envelope analysis, if I can call it analysis, that you did on the last slide, that's what gets you into trouble. So reduced basis methodology says, okay, well, I'm not going to do anything about that. I'm going to try and do something about this. So obviously we could use a smarter sampling method, right? Fabio will tell you about some smarter sampling methods, but let's just say you've picked a sampling method. Your sampling method says I've got to choose m samples. And now this is, we want to try and do something better than this, right? Can we reduce the cost of solving each of, let's say, our finite element problems for the samples that we need? Here's the problem, right? Every time you take a new sample and just stick it into your finite element code, What's the issue with that? Well, I'm going back to the same basis to represent each sample of your PDE solution. That's the problem. Recomputing a new approximation in the same n-dimensional finite element space for each new y of interest is potentially wasteful, right? So that's the issue, right? So the reduced basis method, and I'm not saying this is always going to be a successful strategy. The idea is to try and approximate each of your Galerkin finite element samples of your solution by another function, which hopefully will belong to a lower dimensional space, right? And the work involved in doing that, I'll tell you how to do it in a minute, we'll still need to solve a linear system to get the coefficients that represent this solution in this lower dimensional space, but will hopefully be a lower dimensional problem, little n by little n, rather than big N times big N. Right? So the idea is to approximate each of the samples that we need in a new basis, which is going to be associated with a lower dimensional space, and to get those associated samples, we just solve the coefficients that represent them. And so we'll still have m systems to solve, but they'll be smaller, hopefully. One downside is the original finite element systems are sparse. When we do this reduction, we often end up with dense matrices, even if they are very small. So at some point, you do have to think about the solvers that you use, right? But I'm just going to focus on the reduction aspect. It's a very simple idea. It says finite element solutions associated with smart choices of your inputs can themselves act as basis functions. But think about the sampling method. Let's say you chose, I don't know, 10 different random inputs and you ran your finite element code 10 times. You've got 10 different finite element solutions. Each one of them is a linear combination of your finite element basis functions. So if you take any linear combination of those 10 finite element functions, that's still a linear combination of your finite element basis. So the idea is to use finite element solutions themselves as basis functions. Does that make sense? So conceptually it's very simple. So step one, don't do this, but just conceptually think about the set of all possible Galerkin or finite element solutions to your problem associated with different choices of y. Identify a particular subset, let's say n of them. So this is the hard part, identifying what are smart choices of these parameters. Those new finite element functions become basis functions, orthonormalize them, put them into a set. That's going to be your new Galerkin approximation space. So then when it comes to each new y that your sampling method tells you you've got to solve your problem at, instead of going to your original finite element basis, you're going to find this so-called reduced solution in this reduced space that we've constructed just by writing down the Galerkin equations again. So this is just Galerkin approximation again, but on a lower dimensional space. Right? If little n is smaller than big N. Okay, so what will come out of that is a linear system. I can motivate it in a slightly different way if you're coming more from a linear algebra background. So think about it this way. Solve your finite element system a few times, save the vectors that represent each of your finite element functions, put them in a matrix, column-wise, orthonormalize the columns, then you've got a matrix Q of size big N by little n. So each column is coefficients that represent a different snapshot, as we say, of a finite element solution. And so what we're doing when we solve this system, we get a function, but remember this thing is represented by a vector, in the same way this function is represented by a different vector. What we're doing is representing the vector associated with a full finite element solve with Q times PR, where PR is the vector of coefficients that represent the solution to this problem down here. If we go to our original linear system for our full finite element problem, and we replace P of y by this approximation, put it in and then force the residual to be orthogonal to the columns of Q, then what falls out of this is this reduced linear system, which is what you get if you wrote down the system from that Galerkin equation that I wrote down at the bottom of the last slide. Okay, so you can come at it from linear algebra this way if you want, but this is effectively just the linear system that you get when you write this down. Okay, so we have a new linear system that comes out. The matrix now is this one of size little n times little n. Here's your original matrix sitting in the middle. This is big N by big N, because this one, little n is small, will be a tall and skinny matrix, right? And this will be a short and fat matrix, so this will be small n by small n, and this is like a reduced version of your original right-hand side as well. So this is what a reduced basis method will give you. You can construct this magic Q to start off with. You use it to project your original linear system down onto a sort of a lower dimensional space. And conceptually, this is smaller than your original right-hand side, and this is smaller than your original matrix. The solution is a vector of length little n, and those coefficients represent your reduced solution, which you can relate back to your original finite element vector using the relationship at the top. So the question is, if I solve these systems instead of my original system, can I do it? What do I know about this matrix? Well, the good news is that's symmetric and positive definite, then this one is still going to be symmetric and positive definite, so there shouldn't be any issues with solving the reduced problem. For other situations, that's not necessarily true, but for these scale elliptic problems, everything's okay there. But the crucial question then, well, there's several questions, is how big does little n need to be? Can we always do this approximation and get good error control with a small n? The answer is obviously no, right? The question is, for what problems will it be true? And then the other question then is, well, how do we construct the Q? Right? Let's deal with the first question. So if we deal with these scale elliptic PDEs and we have these Kohn-Lev type coefficients, here's just like a quick and simple numerical experiment that you could do, right? You don't even need to use a Kohn-Lev expansion for this. Just generate some samples, let's say 1,000 or 3,000 samples of your random inputs. Solve your finite element system, your full finite element system, that many times. Take all your finite element vectors, put them in a matrix, and then just compute the SVD of that matrix and find its rank. Right? Compute the rank of the snapshot matrix. So here's an experiment I've done for you, where I've used one of these Kohn-Lev type expansions and I've used two different covariance functions. And I will just say this is a separable exponential covariance, so this leads to random inputs which are not very smooth. And here I'll just call it a smoother covariance, right? Where these eigenvalues decay more quickly. And so what I'm doing here is, well, I've changed J, that's the number of terms, but more importantly in the rows, I've changed the discretization of the finite element space. So I'm increasing N. So the key question is, would the rank of this snapshot matrix increase as I increase N? Is it a function of N? Now, so just pick one column, so let's say I pick this column, right? And compare that with the numbers, let's say, in this column. The numbers are jumping around a bit, and that's because when you compute singular values, right, you have to worry about stability and so on. But hopefully you can see that those numbers don't really depend on N. The rank of the snapshot matrix, as I refine the mesh, is not really depending on my spatial mesh size. If that's true, this gives you an indication that a reduced basis method might work for your problem, because it's really telling you that some of the the snapshots of your finite element solution can really be represented as linear combinations of other ones. If you look at the numbers here compared to here, you'll see these numbers also don't really depend on N, but they are much higher than these numbers. And so, again, as general rule of thumb, these things are decaying slowly. Because you have less smoothness, you will typically need a higher little n to represent your solution well. And that's very hand-wavy. If you want to dig down into the analysis, then you need to look into the approximation theory literature and look up something called the Kolmogorov width. So this is basically a characterization of the worst, so the best, worst case, sampling-wise, error between the full finite element solution and a reduced solution in a subspace of dimension little n. Then really what you want to know is how this decays as a function of little n. Right? A method where a reduced basis strategy is going to be very successful is where this decays really quickly. And that's kind of what's happening here. And where it decays less quickly is sort of happening here. Okay, so that's very hand-wavy. I'm just giving you the method in a nutshell. So how do we compute that Q? If you want to get your hands on this, you've got a finite element code. You might be able to do this relatively quickly. You have to decompose your work into two stages. one that we call the offline stage, one that we call the online stage. Now, as everyone gets more used to machine learning, I think people are becoming more comfortable with this idea that we might just have to do something offline that's really, really expensive, right? Maybe less so 10, 15 years ago. But the idea is you kind of have to sort of, what's the word, organize your computations. Some stuff you're going to do offline, some stuff you're going to do online. So in this context of doing UQ for parametric PDEs, here's what that means. So generally the key philosophy is that whatever you do online, the costs have to be independent of capital N. So for us, that's going to be like the dimension of our full finite element space. And that might be very large if we're working with very challenging coefficients. Offline, right, what we have to do is to construct that magic matrix G to do our projection. And any matrices and vectors that are going to be too expensive to compute online. Online, in this setting, in the UQ setting, means solving all of the reduced basis problems that your sampling method tells you that you need to evaluate your PDE solution for. Okay? So the idea is you build this queue, and then when it comes to actually doing your sampling, rather than calling your finite element code again from scratch, this is like a black box that you just read a new YI into, and then you get this new reduced solution out. Okay, but you have to reorganize your computation so that nothing that you do here depends on capital N. Okay, so people fight about this. The question is, can you make those computations cost independently of big N? If you remember, you've got this matrix here, which is big N by big N. So if solving this problem means you have to assemble this matrix, multiply these things together, that computation is not independent of big N. So unfortunately, it means you need to request more structure in your problem. And either your problem already has it, or you have to make it have it. Right? So if you have one of these coherent lab expansions, the good news is you already have it. It says your system matrix for a new choice of Y can be decomposed that way. It just falls out of the definition. So that means when you compute this projected matrix at the top, right, for a new choice of Y, your system matrix already has this form. So if you were to substitute that in there, it means you can pre-compute this offline, so that's the bit you do offline, and then every time you need to compute a new system, basically you just take a linear combination of these matrices that you've already computed. Right? So if you have this is why people like these affine coefficients in this world. If you don't have that, then you have to introduce an extra layer of approximation, which I won't go into, which decomposes your matrix, and this is now a further level of approximation, into an expression of this form so that you can do this rearrangement. And this is often called, I've got this in brackets, depends which community you come from, it's the same thing effectively, empirical interpolation or discrete empirical interpolation. So there's a paper there, you can follow up on that if you wanted to. So go through this relatively quickly, but then how do you compute this Q? And there are different strategies for doing this, some more sophisticated than others. So I'll just outline what's typically called a greedy method. And so basically this idea is that you compute this matrix to do your projection one column at a time. Okay? Usually using some sort of optimization or accuracy criterion as you go along. Okay? And you'll notice some of the terminology is just kind of very similar to what we do for machine learning methods these days. You need a training set, right? You need a training set. So you need some sort of samples in your set gamma to test this on. You're doing it in what we call the certified way. You need an error estimator for the error in your chosen norm between your full solution and your reduced solution for a fixed choice of Y. So here's what you do. You kind of start with some sample of your Y. You go and you solve your full finite element system for that sample. You've now got one finite element solution. So your Q matrix just has one column to start off with. So then for all the Y's in your training set, you go and you solve the reduced problem, and you assess the error somehow between your full solution and your reduced solution, having a Q with just one column, you say, is that good enough? Usually won't be. So you find the Y that's the worst offender, which leads to the biggest error, and you say, okay, that finite element solution associated with that Y is not well represented with this reduced basis. So I need to solve my full finite element system for that Y and make that a new column of Q. And so you sequentially add more columns to Q using the worst offenders, if that makes sense. So at the end of it, what you should have is a Q which is good enough for all the Y's in your training set, if that makes sense. Okay, so that's the general strategy. So if you followed any of that, then conceptually, that's a strategy for reducing the size of your system solves that you could embed or incorporate with any sampling method that you have. Reduced Bayesian strategy is that you don't touch a sampling method. I'm just going to try and reduce the cost of solving the samples of my PDE. Okay? So we could, if we wanted to, and people have done this, is just combine it with a Monte Carlo method like we had before. You said, okay, because I'm starting in this parametric setting, my solution P is a function of x and all of these parameters, however many I've got. So let's say I was only interested in computing the expectation of the PDE solution. Okay, you can't get your hands on P, so first thing you do is you replace your P with a sort of a finite element type approximation spatially, right? And you can't sample, so in the finite standard Monte Carlo setting, you would just take samples of your Y, take M of them, you call your finite element solver and you just average them. That's what we did last time. But now we could, right, instead of solving your full finite elements system, you could just replace that with a reduced basis solver. So now there's kind of three levels of errors. Your finite element discretization error, your Monte Carlo sampling error, and now you've got the error between your finite element solution and your reduced basis solution. So this is all amenable to analysis for the simple elliptic problems that I showed you about. Okay, so we could do that, and we could go into the analysis and show you why this might be better than standard Monte Carlo. I'm not going to do that though. I thought this might be an opportunity to tell you about a potentially smarter sampling method than Monte Carlo. Something called the stochastic collocation method. So view this as just still going to stick with standard finite elements, but I'm going to try and do a potentially smarter sampling method than the Monte Carlo method. So in a nutshell, this is going to be some form of interpolation. So we're going to have m sample points again. So let me call my sample point z1 up to zn. These are going to be some set of points in my parameter domain. And the difference is these are not just going to be randomly sampled like they are in the Monte Carlo method. In the stochastic collocation method, what we're going to try and do is pick some points and construct an interpolant on the parametric domain, if that makes sense. So we're going to compute an approximation which has this form. So these things are going to be Lagrange polynomials in j dimensions associated with the points that I'm picking. And the idea is, like a Monte Carlo method, we would solve our PDE system at these points. Again, the strategy for choosing them is different. We have to solve finite element systems at these points to get the coefficients in this expression. But after we've got them, we're not just going to average them. We're effectively going to construct a polynomial approximation in the Y. So we're going to interpolate with a sample of the Y's, we'll get some finite element solved, and then we're going to interpolate over the whole parameter. Does that make sense? So it's going to be a polynomial-based approximation. And hopefully you can see that this is what's known as a surrogate, because if we can build this, this is a function of Y. So if I want to, after I'm done, query this approximation for a new choice of Y, I could just stick the new Y's in there, and as long as I can evaluate these functions for new choices of Y, I can query or approximate the solution to my problem for a new sample of my inputs without solving any more PDEs. Okay, so this is an example of a surrogate learning approach. So, again, this would be the standard way to do it, but I could replace those full solves with reduced basis solves, right? Because reduced basis methodology is sort of simple enough that I can wrap it around any sort of sampling technique that I want. Let me just pick that apart a little bit more. So before I add the reduced basis stuff into it, so here's standard stochastic collocation. So the idea is I take my parametric PDE solution, and now I'm going to approximate it by the interpolant on the parameter domain of my finite element approximation, right? So the work involved is still solving m finite element systems of dimension n at this stage, where n is the dimension of my Galerkian finite element space. So if I go through this strategy, then unlike the Monte Carlo thing, I've got finite element error as I had before. The other contribution to my error is no longer Monte Carlo standard sampling error, it's interpolation error. So the theory for this kind of approximation is completely different. Because we assume this is a good strategy. Is it a good strategy? If I'm approximating the solution to my model as a polynomial in my y's, and to get good error bounds, then I'm going to need some assumptions on the smoothness of p with respect to the y's now. Not just the x's, which I need to get a handle on the finite element error. I'm going to need some information about the smoothness as a parametric object, right? So to dig into the theory, this is kind of the first thing you need to look at. So just a word on computation. So as I said, at the level of implementation, it is sort of non-intrusive because all I've got to do is compute those coefficients in blue. I have to solve all these decoupled systems. At the end of the day, we have a function. So at the end of the day, I want to compute statistics. So maybe I want to compute the expectation of this approximation. And that's an integral in which this probability density function occurs. And that can be done with quadrature. Right? So that's fairly straightforward. If you want to dig into the approximation theory associated with this way of building a surrogate, then as I said, Fabio is going to be here later in the week. So him and his collaborators, Raoul Temponi, Ivo Boguska, sadly no longer with us, they had a suite of papers on this stuff in the sort of around this era, 2007, 2008, and so on. There's also another paper by Jürgen Hesthaven, appeared around the same time. This one is a bit more computational, I would say, in nature. This one is more heavy on the analysis. And so this sort of suite of papers popularized this methodology in the UQ community for these kinds of problems. So they filled in the analysis for this part and sort of combined it with sort of things we already know about finite element error. Okay, so a priori error analysis is available for this kind of approximation and for these problems. But I'm not going to go into it. So if we want to do this, then obviously we've got to first of all decide, before we worry about the cost of getting these coefficients, is what's a good choice of points. Right? This has to be guided by interpolation theory now. What is a good choice of interpolation points in j dimensions, where j may be 10, maybe 20? If it was 100, that would be really bad. So the higher j is, the more challenging this is going to be, obviously. So there may be a limit to how far we can go with a dimension to kind of use this sort of strategy. Right, so don't know how much people know about interpolation and quadrature theory in high dimensions. Well, we always start with what we know in one dimension, right? At least I do. Just to say, the headline news is, in case you weren't aware, constructing accurate approximation schemes in j dimensions needs thought. But typically, we build them up by using, leveraging, combining in smart ways schemes from one dimension. So what we'll typically do is start with a family of schemes which have some parameter that we can twiddle that will somehow vary the accuracy of the scheme. So I'm going to work with sets of interpolation points. Let's stick to interpolation, which I'll call Z alpha, in one dimension. So let gamma 1 just be an interval in one dimension. Pretend we've got one parameter to start off with. And I need a good set of interpolation points in one dimension. So the idea is alpha will control the level of accuracy of the scheme that I choose. And the number of points that I will need will depend on alpha. So change alpha. If alpha's 1, you have n1 points. If alpha's 2, you'll have n2 points, and so on. So in one dimension, I hope most people have heard of at least one of these schemes. Gauss points, Chebyshev points, Clenshaw-Curtis points, right? So to compute statistics, we will need integrals which have our probability density functions sitting in there. So Gauss points are a good idea because we have weighted integrals. If we're working with uniform random variables, anybody know what the probability density function is for a uniform random variable? It's the constant, right? So that's the EVK, so that can always come out with the integral. So for uniform random variables, no big deal. Other kinds of random variables, we have more complicated probability density functions, but let's just deal with the uniform random variables. So Clenshaw-Curtis points, for instance, tend to be a nice thing to use for uniform random variables. You can just open a textbook. So quick visual here, I'm just showing you Clenshaw-Curtis points on the interval minus It is minus 1, 1, yeah. And I have schemes where I've got an accuracy parameter alpha, going from alpha is 1, which is a 1-point rule, alpha is 2, which is a 3-point rule, alpha is 3, which is a 5-point rule. So these are almost doubling up. What you should be able to see for this scheme is I increase alpha, the sets are nested. So this point is included in this set, and these 3 points are a subset of these points, and these 5 points are a subset of these points. Okay, so in one dimension we can do interpolation with any of these classical schemes, and the accuracy approximation is obviously going to depend on how many points we use, but also you should know the smoothness of the function that you're trying to interpolate. So in high dimensions, I'm not going to get into a lot of detail given the amount of time that I have. I'll make the slides available and you've got more of the maths in it if you want to follow up on it. In high dimensions, well, let's just say in J dimensions, what can we do? If we've got a scheme in 1 dimension, what's the easiest thing to do? If I want to go from 1 dimension to 10 dimension, we just take the tensor product of that rule in each dimension. Okay? That's what we call tensor product rule. We end up with grids that tend to look like this over here, right? Sorry, this is 3 dimensions, obviously, right? If J is much large, let's say we take 10 points. 10 points times 10 points times 10 points times 10 points, right? The number of points that you use is going to be very large. So at some point in the UK community, people rediscovered some approximation theory from the 60s, which is something called sparse grid interpolation. So sparse grid interpolation, or sparse grid quadrature, can help you if the number of dimensions that you have is really, really large, or not really, really large, but moderately large, and you have enough smoothness. So I just want you to, first of all, look at these 2 tables. This one is related to a tensor product grid in J dimensions, as I'm increasing the number of dimensions, from 2 to 5 to 10. And here I have some sort of parameter which is controlling the polynomial accuracy of my interpolation rule. So let's say we're in 2 dimensions, and I want to create an interpolation rule which is exact for polynomials of total degree 4. I need 5 points in each direction, so I need 25 points. Sparse grid rule, 65 points, that sounds weird. We go to 10 dimensions. The one polynomial accuracy of degree 4 in 10 dimensions, I need a rule of 10 to the 6 points. With smart sparse grid rule, apparently I can do it within 8,801 points. Right? Sparse grid rules, like the name suggests, can deliver the same polynomial degree of accuracy as a tensor product rule can, with much fewer points in higher dimensions, right? As long as we have enough smoothness. That's all I will say at this point. But you'll notice there aren't really significant savings until you get to, I think the key dimension is about 6, where you start to make some savings. So I'm not going to go into that, I'm just saying, right, if you want to use this thing called stochastic collocation, right, we're going to choose some interpolation points, and the way to do this is not to use a tensor product grid. But the success of this depends on what you know about the smoothness of the solution with respect to those parameters. So I promised we'd have a discussion session, so I don't think it's worth me going into the theory associated with this now, or how these grids are constructed. I'll just leave the slides with you and you can follow up later if you want to. I'm just going to show you some of these methods in action, and then we can have our discussion. Okay? So, try example. Let me go back to the first PDE model I wrote down today. There's my groundwater flow problem. I've got a K, which is random. And I've done the thing that I've said. I've reframed it as a parametric problem by representing that random field as one of these series expansions and then truncated it. So you can see I've got no omegas, so now everything's in a Y. Gamma's in there somewhere. So the spatial discretization, I'm using finite elements, standard finite elements. And I'm going to not do Monte Carlo, like I said. I'm going to use this kind of stochastic collocation method so that I actually construct a polynomial-based approximation as a function of y. I want to construct a surrogate. But now, instead of solving the full finite element system as if I was using the conventional method, I'm going to approximate, I don't know why I keep pointing, I'll just do this. I'm going to approximate the finite element evaluations with reduced basis solves. So I'm going to do this offline thing where I construct this reduced basis, and I'm going to evaluate reduced system, I'm going to solve these reduced systems to get the coefficients, and then plug them back into these expressions so that I have the polynomial-based approximations to my two solution fields. So I very quickly, oh my goodness, what happened there? Oh no. I'm hoping I didn't just delete something important. Okay, no. Okay. Okay, so in the offline stage, just a couple of points. So the way I outlined the reduced basis method made it sound like really easy, and there was nothing to worry about when you take the cue when you construct your reduced problems. When you have symmetric and positive definite problems, you really don't need to worry. For this problem, because I use something called a mixed finite element method, the linear system I have to solve is indefinite. The saddle point problem, so this projection and the way you do it needs more thought. But the good news is many people have thought about this and there are techniques for doing this. So it's not as straightforward as how I outlined for the scale elliptic problem. What do I use for my training set? Well, the good news here is I only need my reduced approximations to be good for my chosen collocation points. So it's not like I just choose an arbitrarily big training set. I'm only constructing it so that the coefficient approximations are good for the ones I need. So that's good. So I'll just show you two quick toy problems. One's very easy and lower dimensional. So here I just have a coefficient which is piecewise constant. It's not really covered in love expansion anymore. So it's just a spatial domain which is decomposed into 5 different subdomains. So my coefficient is just piecewise constant for uncertain in each of those 5 subdomains. So it's characterized by 5 parameters. I've used a finite element, standard finite element mesh. So big N is actually not very big. It's only about 2,200 and something thousand. So I'm showing you the mean velocity field and the mean pressure field as computed by my mixed finite element sparse grid interpolation reduced basis method. Right, so I'm just going to show you some information about the computational effort required. So not accuracy, just computational effort required to do this. So at the top, there's just some information about the offline stage. So remember I said, in the offline stage, what we're trying to do is craft this matrix that will do your projection with some accuracy control. So here's my accuracy parameter epsilon. So as I ask for more accuracy, then obviously the dimension of the reduced basis that I need needs to grow. Right? If you want more accuracy, you have to do more work. So this is now going to be my little n. So this is the time to solve my full finite element system, and since that wasn't very large, that's just 2 seconds. But if in my sampling method I need to do this 1,000,000 times, that's still a lot, even though each one costs me 2 seconds. And here's the time it takes me to solve a reduced system of this dimension. So clearly if I just compare these timings with this timing, you see that there's a saving here. Okay? So the cost to solve one reduced system can be much smaller than the cost to solve one full finite element system. But I'm not just interested in solving one system, I'm interested in, let's say, computing things like means and variances of my solution fields to do my UQ. We'll wrap everything together. So what am I showing you here? So what I've done then is chosen a particular level of accuracy for the stochastic collocation part, so that my solution is a sort of polynomial of a certain degree, if you want to think about it that way. Here's the final full cost of my full finite element solves with my collocation method if I was using the full finite element method. So let's just take the last line. So here's where I fix the degree of accuracy for my reduced basis method, so 10 to the minus 5 in this case. So this is the sort of the accuracy parameter for my stochastic collocation polynomial approximation. So that has 5,503 points if I use one of these smart sparse grids rather than the tensor product grid. So to implement this, I have to solve 5,500 finite element systems. We do it the full way, right? Don't use parallelization or anything. That's how many seconds it's going to cost me. I use my reduced basis method. Offline, that's the cost to construct the reduced basis to that level of accuracy. My online solving the same number of systems as I did over here, that's now reduced a lot. Okay? And even if I add in the time to do the offline thing, speed up's a factor of 10, right? So that's good. But this is a very easy problem. It's very easy because I have 5 parameters, right? So I don't have many parameters, and also I have an affine expansion for my coefficients as well. Just quickly contrast that with a problem where you have non-affine coefficients. And so in this scenario, you have to do this extra step of decomposing your system matrix in a way that allows you to decompose the costs of your offline and online business. So now you have the cost. This problem has 12 parameters, so it's a bit more challenging in that respect. So this is the cost of solving one finite element system on my chosen finite element mesh. Again, that's fairly quick. But if I use the reduced basis approach, again, I'm varying the parameter epsilon, which controls the level of accuracy. Here's how the dimension of the reduced basis has to grow again. But k is the number of terms in this extra affine expansion I need to do on my system matrix. And what you see is this may be much larger. It may have to be much larger than the number of parameters I originally had to meet my accuracy requirement. So this extra business that I have to do to make savings online may actually, require me to do much more work offline in order to ensure that my online part goes well. So these are the times to solve the systems if I don't use this dime business. The cost then will actually increase as I refine my mesh, actually, and then the times in blue are the system solves if I actually use this dime thing as well. And again, if you compare the numbers in blue with these numbers, then you see that we can get significant speed-ups. But again, bottom line down here, if you compare the full time to use a stochastic collocation scheme or a sampling method that requires me to solve this many systems to get a certain level of accuracy. That's how long it takes me, in theory, with my full finite element method. After I've constructed the reduced basis, then to solve the same number of reduced systems to some accuracy, obviously is much quicker. Compare these two numbers. But this is the offline cost. If I add these two numbers together, then not such a big speed up when I actually say, okay, hang on, I have to do all this work as well. But if this was somehow just something I could do and forget about, then clearly there's a big difference between the two. Okay? And then finally, this is my final slide. So obviously I haven't said anything about accuracy. I've given you some references where you can dig into the approximation theory and get error bounds. I will just kind of show you something visually on this slide. Although I forgot to say it. So in this experiment, the coefficient was non-affine because it was the exponential of a random field. And it was still a very low-dimensional random field, which only had j parameters in it. Completely cooked up example. I just wanted to show you this, because what I'm showing you here is some assessment of the error between, well, where am I showing? Okay, so I'm showing you the error between the full solution, the error in the expectation of the pressure on the left and the velocity as a function of the dimension of the reduced basis. So this is kind of like characterizing the error associated with just the reduction part. So this is like little n, if you like. And so the question is sort of kind of get away with a small n or not. And what I'm showing you here are results for 4 different expansions where these things decay at different rates. I won't kind of tell you all the different covariance functions I've used. I'll just tell you that the one at the top is not very smooth, the one at the bottom is very smooth. So I mentioned the Kolmogorov width before. This is associated with that phenomenon. For this class of problems with these types of coefficients, there's rigorous analysis that shows you that the Kolmogorov width decays as a function of little n, right? And the smoothness, so the convergence rate is directly related to the smoothness class of this. So the more smoothness we have, the faster those eigenvalues decay. So the purple line, somebody asked me earlier about exponentially decaying things. So this line, the eigenvalues are decaying exponentially. And that's why in this scenario, the reduced basis error is sort of converging very quickly with little n. Whereas for the blue line, where these things are decaying much more slowly, then we have much slower convergence. This is typically what you will see in this very hand-wavy sense. I hope I've illustrated this. The faster those eigenvalues decay, the more smoothness we have, the more effective and the more successful these methods will be, and the more computational savings potentially can be made compared to just standard sampling methods used off the shelf. Okay, that's all I wanted to tell you in this session. So what have I done? I reminded you a little bit about Galerkin approximation. Maybe I'll go back just quickly to the slide I showed you right at the beginning, just to wrap up, so that Rob also knows what we talked about before we have our discussion session. So we framed my random PDEs as parametric PDEs. Once they're reframed as parametric PDEs, I have other methods and Monte Carlo methods that I can use. I very quickly, and I appreciate it was quite quick, introduced you the concept of doing a reduced basis approach, which you can wrap or incorporate with any sampling strategy that you're incorporating with a finite element method. I very briefly told you about stochastic collocation, which produces a polynomial type approximation in those y parameters. And then tomorrow I'm going to tell you about this thing called the stochastic Galerkin method. So hopefully I've told you a little bit about some methods without going into too much depth. And then if you want to follow up on anything that I've said with the slides, then you can find the references that I've given. Okay, I'll stop there.